Suppose we have an experiment, or we've got some sort of data where we have a set of y versus x data points. And what we want to know is what's the trend of this data. We expect that these data points were observed with some uncertainty, and that there's actually some trend that goes in the middle of these data points, and maybe that trend is linear. Assuming that we have a linear trend, we want to consider the distances, the vertical distances of these points from our linear trend line. So each point lies some distance above or below a straight line. Our best line is going to be the one that, in a sense, minimizes these distances, minimizes the average distance. So I'm going to say minimize average distance. Is that what we're going to mean by our best trend line? It turns out that not quite. We want to minimize the squared distance. So we could say, in a sense, we minimize the average squared distance of the points from the line. So not quite the average distance. We minimize the average squared distance. Now, we're going to minimize the average squared distance if we minimize the total squared distance. So we're not going to bother averaging the squared distance. Equivalently, minimize the total squared distance. The question becomes then, what is the equation of the line that accomplishes this, that minimizes the total squared distance of the points from the line? If I stretch a string, or in this case a wire lead, between these points, we're pretty sure that the best line is going to be somewhere in here, but we don't know which line is the best. So a straight line can be controlled by two parameters. Most often we're going to use the slope and the intercept. So let's assume that the equation of the line is y equals ax plus b, a being the slope, b being the y-intercept. In this example, we've listed 4 points, so let's just assume we have 4 points. x1, y1, x2, y2, x3, y3, x4, y4. Once we see what happens with 4 points, it'll be easy to understand what happens when we have more than 4 points. Our vertical distances well, let's back up a second. Let's say the vertical coordinates on the line corresponding to x1, x2, x3, and x4 are what? y1 equals ax1 plus b, y2 equals ax2 plus b, y3 equals ax3 plus b, and y4 equals ax4 plus b. You might be able to see everything up to that edge. And now I've got a little bit of a discrepancy. I've got y1, y2, y3, y4 here, y1, y2, y3, y4 here, and these are our observed y values. These are the y values that would be predicted by the line ax plus b. I'm going to need to do something to distinguish these y's from these because they aren't necessarily equal. In fact, we pretty much assume that none of them are equal. To make the distinction, I'm going to put hats on these y's. So if this is our first point, then this point is x1, y1 hat. This point on our line is x1, y1, which equals x1, ax1 plus b. The distance, the vertical distance, is y1 hat minus y1. And let's just, since we're going to be minimizing the squared vertical distance, the squared vertical distance is this. If I really wanted to call this vertical distance, I'd have to put absolute value signs around it. So I'm just going to square it so that we don't have to worry about whether it's positive or negative. Okay, so our squared vertical distance is this. Now we don't square it just for that reason. We square it for certain statistical reasons so that we'll have normal distributions of uncertainties and errors and so forth, and you don't want to get into that right now. You would use the techniques of this course to understand why we use the squared distance, but you would do that in a statistics course, and we're not going to get into that detail here, normal distributions and so forth. We have the tools to do it, it's just that we don't have time to do it. Now, each of these points has a similar expression for the squared vertical distance. So I can say that the total squared vertical distance is what? Now let me back up. I said y1 hat minus y1 squared. That's going to be y1 hat minus ax1 minus b. Because of course y1 is ax1 plus b. When we subtract y1, we get negative ax1 plus b. Every point is going to have a similar expression, except we'll have subscripts of 2 on the second point, 3 on the third point, 4 on the fourth point. So the total squared vertical distance is going to be what? It's going to be y1 hat minus ax1 minus b squared plus y2 hat minus ax2 minus b squared plus y3 hat minus ax3 minus b squared. And since we don't have room, we'll come down here and do y4 hat minus ax4 minus b squared. Now remember that x, and that should be x1 comma y1, y1 hat, okay? X1 and y1 hat are quantities that we've observed. So these are numbers that we're going to know. The question then is, how do we find the values of a and b that minimize this expression?